So, what did I do this week? First thing, I went kayaking. And then the second thing is I did some science. And this video is about the science part. So if you're new here, welcome. My name is Jess. I'm a mechanical engineering, combustion engineer, converted into environmental engineer. And I'm doing my PhD in sediment transport. And as part of my PhD, I'm building a cheap but reliable and accurate turbidity sensor. So I've come up with a few different designs of my sensor, and my goal is to test them and then select the best one. So in this video, I'm going to show you how I designed the sensors, the different sensor versions, and that all starts with 3D printing the very first piece of my sensor. It's Tuesday, April 21st. My professor's daughter has a 3D printer, so they 3D printed the first part for me. It actually really looks really good. I mean, this is terrible quality, my phone. So this is the principle. So I have this LED and I really need it to be aligned in this chamber. So the plan is to put it in here, and actually it fits perfectly. I will probably need to put some epoxy to really make sure this is sealed. But it's really, really stable in there. That's the first thing. Then the second things are, for example, so here the plan is to put one of these low pass filters, and they fit perfectly in here too. Then the one thing that doesn't really fit at the moment are these plano convex lenses. So to put those in, I put them in this way. I didn't really put a tolerance for these plano convex lenses because I really wanted it to be sealed, but because the filaments of 3D printers are, you know, like the holes are kind of jaggedy, it actually doesn't make any sense. Instead, what I should do is put a little tolerance and then fill the holes with epoxy. So now I know, and now I'm going to remake this design a little bit so that it's really perfect, and then I will resend him the new design, and at the end of the week I will have my new design. I will assemble it, I will attach my microcontrollers, I will take this tubing, I will just glue it on top, and then I will pour different liquids in here, and we will do the first test of my sensor next week. So now with this first assembled part, what I did was, as I showed in that clip, is put together all of the different small little components. That's LED, the detector, epoxy the tube on. So basically I built the first version of the sensor. It's not waterproof, it's not able to store data or anything, it's just able to output turbidity as a frequency. So to convert frequency, the frequency that I'm detecting using the light detectors, to turbidity, what I planned to do was use different dilutions of known NTU value, pour those into my sensor, and then try to calibrate my sensor this way in order to get a linear relationship between NTU and frequency. I started off by doing that using different milk dilutions. So I just diluted a bunch of milk and then measured its turbidity. I am almost ready to do real experiments. I'm back in my office, my plants, everything is here except no one is in the office because everyone is doing modeling at home. So what am I doing now? I am preparing different samples with my expensive turbidity meter, which it's taking samples right now. So I'm not going to take it out of the water. I'm going to see if I can prepare different turbidity samples using milk. So that's what I'm doing right now. I'm just diluting milk and then measuring what the readings are, and then those samples will be the samples that I will try to match with my sensor, which hasn't been built yet. So this tells me that right now the NTU reading of drinking water is around 0.5, which is the same as the river, by the way. And next, I'm going to prepare a sample with milk and see how much more turbid this is. Okay, something that's pretty cool is that this 3.5% milk actually says it gives like almost 5,500 NTU, which means I won't need to purchase formazine, or whatever, something that goes up to 4,000. I mean, it would be good just to make sure this sensor is working correctly, but the manufacturer said it is, so I should be able to trust this value. Now let's dilute this milk in half with water. Okay, it's Wednesday, May 20th, and this is what I've been doing the entire day. I've been diluting milk in water and measuring its turbidity, and then yeah, so I've just been trying to make different samples. So I have these aren't specifically in order, just in order of when I did it today. So here are my different bottles from 1 through 7, different turbidities using the expensive measurement, and then these will be my samples used to test my sensor, which is not assembled yet. Okay, May 25th, different day, same outfit. I got my 3D printed pieces from my professor. I realized that the inside of this is white, and so when I have my LED shining in here, probably the reflection will not be so good from the white chamber. So I bought some paint, acrylic paint, which apparently once it dries, it's not water soluble anymore. So I'm just making some, I'm just doing some art, you know. So I went kayaking on the weekend. When I came back, I remeasured some of the milky bottles, and I've actually been getting some different values. Like for the exact same water, here, let me show you. This was the original turbidity values of one of my water bottles, pretty large range. But then I took the bottle out of the fridge, and this is the range I got. These numbers are they're like, this is way too large of a difference. So then I thought maybe the turbidity of milk depends on temperature. So I let it cool to room temperature, or I started to let it cool, and it started to drop again. Now I'm kind of doing a little mini study measuring if the turbidity of milk changes with temperature. Who cares about this? Nobody on the planet except me. But unfortunately, the milk was not stable enough, so I switched to iced tea. And then it turns out that the iced tea was also not stable enough. So I decided to actually move ahead and purchase this expensive, super carcinogenic chemical called formazine or formazine. If you know how to properly pronounce that, please leave it in the comments below because I cannot figure it out. Anyway, this formazine is supposed to be ultra stable, so that's why I bought it. Then, just to make sure that the formazine was ultra stable, I started to measure the formazine, again using my expensive sensor, the same one that I was measuring the iced tea with and the same one I was measuring my milk with. So I'm actually super frustrated because I got this formazine to use as a calibration solution, basically to see how accurate my design of the sensor is, and I don't know how to use it. I measured, that's the formazine, I measured using the expensive sensor. The level, it's supposed to be a 4,000 NTU sample, and I did the measurement and it was 3,400. And I was like, okay, it's fine as long as it's stable. I know it's 3,400. I did all of my measurements, which took like 3 hours for 4 different designs of my sensor, and then I poured the sample back out and remeasured it, and it was 3,500 NTU. So it changed by 100 NTU, and then that's like not okay, first of all. So then I emailed the company, and now they're checking if they gave me a bad batch, which would be annoying if it is a bad batch, because I mean, first of all, it would be cool because the that would solve my problem, but it took like 6 weeks for this stuff to arrive, so that's just really annoying. But then it turned out that my formazine was actually not stable either. So I had to stop my experiments, and I got really frustrated because I had no idea what to do next. My entire calibration procedure of the sensor was based off of using a stable substance and calibrating the sensor. So it's a week later, it's 5 p.m. I've been doing experiments the last 2 days. I've moved away from measuring the formazine because no sensor is capable of reproducing proper NTU values, which I guess is good news for me because it means I don't have to be so accurate. But also it means that you just have to trust the formazine. So I just dilute the formazine according to the manufacturer's instructions, and then I pour it into my sample cells and take the measurements. I found someone at our university that has actually used a lot of these really expensive turbidity sensors. He basically did an entire PhD on it, and I talked to him. I read some parts of his dissertation, and it turns out none of the expensive sensors are accurate above like a few hundred NTU. If you get one sensor from a company and another sensor from another company, and you put them both into a substance that is supposed to be 500 NTU, neither of them will read 500 NTU. Maybe one of them will, but most likely they're going to be way off by hundreds of NTU values. And he even found in his PhD that if you take one sensor from one company and the exact same model, the exact same sensor from that exact same company, and you put them both into a substance that has, for example, 600 NTU, they could have different values. They could give you different readings. Anyway, this video is not about all the other sensors, it's about my sensor. So while I was resolving all of these formazine and milk and whatever problems, I started to work on version 2 of the sensor. And so it just has a few little different things here and there, like a shorter tube, more accurately placed lenses, little things like that. So the procedure for my experiments is as follows. So here I have 2 pipettes. I use this one to handle the formazine, and I use this one to handle the water, deionized water, which is right there. Here's first sample cell, second sample cell, and then here's number 4 and number 3. So the way I'm doing this is I dilute the formazine. So I have the different formazine dilutions here. What I do is I pour them into one of my sample cells, which has an LED, and then the 2 detectors right here. And then I connect the LED and the detectors to my little breadboard setup. So I have the resistor for my LED, I have some decoupling capacitors for the detectors, and it all is measured by my ESP32, which I've programmed to have 2 timers so I don't have to use 2 Arduinos. So this one has at least 2 timers. It measures digital frequency detected by these 2 detectors. And then I just put an Arduino additionally to one of these detectors. So you can see the Arduino takes the detector signal, and then also the ESP takes the detector signal. I'm just checking to make sure that this program is properly counting the digital frequencies. So right now I diluted 4,000 NTU formazine to 800, and I am just about to connect all of these wires. And then what I basically do is, for each of these sample cells, the difference between them is, so for example, this one, it has no lenses inside, so it's just the detector going through the sample cell, straight up detecting. Then the next one, you can see there's a lens, so it kind of narrows the field of vision, so all of these have lenses. These 2 and this one has lenses. Then what I do is, after I do all those measurements, then I pop in some infrared filters, or sorry, some low pass filters. So what I'm trying to do is see which one of these architectures is the best and the most accurate. Now I'm just letting it sit for like 5 minutes so that the bubble, like there are no bubbles that will influence the results. Doing all of those measurements at 1 NTU value. So right now, 800 NTU takes 2 hours. So yesterday I got 2 data points. Today I got, what day is it today? Okay, I did 2,000, I did 1,000, and I'm at 800 and it's 5 p.m. So now you can see the detector wires are connected and the LED wires are not connected, and I'm taking measurements, both my Python program and the Arduino. And the reason the LED isn't connected is because I actually take 2 measurements for each of these variations. The first one is without the LED on, and the second one is with the LED on, so that I can kind of subtract the extra noise, extra light noise that's leaking through into the sample cell, or that is internal reflections within the sample cell. The frequency that is output out of my sensor for the different NTU values, then I create a curve for this frequency versus NTU. I create a relationship, a curve from that, and it should be a linear relationship. So I spent a long time doing these measurements, and what I found out is that I have a huge source of error, which really sucks. So I think the last time we spoke was Thursday evening, where I was saying I need 2 hours for one data point, and I spent the last 2 days getting data. What I realized Thursday evening after vlogging to you guys is that there was a huge error in all of my data. So there was some sort of source of error. How did I know that? If I was measuring and I put a cover on and I took a measurement, and then I took the cover off and I took a measurement, this case should have more light coming in clearly because it's open. This case should have less light coming in. And that wasn't happening. I was having more light like this and less light like this. That makes no sense. So Friday I found out it's just that my, first source of error is that sometimes if I poured the formazine not correctly, it would have bubbles in it, and the bubbles would affect the measurements. And then secondly, if the LED was not super stable in the cell and it moved, it affected all of the measurements. So today I restarted, it's Monday, I restarted the measurements. It took me the whole day for one data point. I want to get 10 data points. So at this point, either I reduce the number of data points I need, or I just suck it up and do these experiments for the next 2 weeks. We'll see. So yesterday I forgot my laptop charger, like a bimbo. So I tried to make all of my programs work with Windows computer from our lab, but I had to download Python and all of these other, like a USB drivers particular for this microchip, and in the end I didn't have like administrative rights and all of this crap. So I went home and I worked on my research proposal, which is something else we have to do in this university. After 1 year, you have to compile basically what you think your PhD will be about, and present it to a panel of expert judges, and then they will decide if you, I just realized the camera's on this side, and they will decide if your project is cool enough to do a PhD and interesting enough. So today, it's Wednesday, and I'm working on data point number 2 with 4,000 NTU. So this goes in here, and then I start my measurements, and hopefully it only takes half the day, and then I can do another measurement to make up for yesterday. So it's 10 a.m. August 6th. I've been working all week, as you saw, taking measurements with my latest device, using the formazine. I noticed I still have a lot of fluctuations in my data. I don't know, my frequency that I'm measuring is not constant. And it's not influenced by noise because it's not a little jitter. It's going down. So I really have to debug today. I think I have to move away from this breadboard. I have a little prototyping board. I think I'm just going to quickly solder everything with short leads, or leads. I think it's leads. Right now I'm just studying for an exam. Yes, still have to take an exam as a PhD student. So this course I'm in is called River Morphodynamic Modeling. So here are some of the equations. Look at that, 2D modeling with uniform sediment. We have some, conservation of sediment, of mass, water mass conservation. This is momentum, hopefully, or else I don't know what I'm talking about. So I just finished studying. I'm back in the lab. I have a few ideas of what I could do. The first thing I'm going to do is I'm going to repeat my experiment from last night to see if I actually have this drift in data or if I was just too tired and hungry. The second thing I'm going to do is I noticed that if I moved any of these wires, I got a change in frequency, and probably that has nothing to do with the drift, but maybe it does. But anyway, then if I move them minutely, I get different values. So I'm gonna check that, and if that's the case, then I solder everything onto my prototyping boards. So that's the first thing I'm gonna do. The other thing, and then I'm gonna try with a lot of different detectors because I just had a bag of detectors that came in, and yeah, maybe it's just the LED in the detector and I just need to try a different one. It still drifts. Then I'm gonna try with deionized water and see if I can get stable results. And then I'm also gonna try with air and see if I get stable results. And if I don't and I have a drift, then I know it's not the formazine, it's the setup. So my next step is to solder everything together and move away from the breadboard and just redo the experiments using the formazine, and then hopefully I will have real data which I can show you. So I'm really sorry I didn't finish the experiments in time for this video, but I figured it was better to output a video than it was to wait to finish the experiments, because that's what I kind of did. And then it's been 4 or 5 months since my last video. So hopefully the next video I make, you will see that you will see my new soldered sensors, sample cells, and hopefully I will have data, and then I could share it, and then yeah, we can move on from there. I hope this was interesting. I hope you liked it. If you do like it, then do the like thing below and do the subscribe and the bell. And just all of those things. Remember to subscribe, because then you'll find out what happens with the next sensor. And don't you want to know that? Or are you just bored and you would rather see kayaking next time? Also let me know about that. Thanks so much for watching, and yeah, see you next time, hopefully. Unless I quit. I'm just kidding, I'm not gonna quit. Let's hope not.